So the number of assets are going to increase. And then the number, the needs for communications are going to increase. And that's where networking, it becomes a requirement. When the number of access becomes so large that addressing each of one of them individually with an individual link becomes too expensive, too difficult, you need a network so that you can move across them or move bytes and bits across them more easily. And in all wisdom, the different organizations, starting with the space agencies and then the commercial industry and other organizations, decided that it was good to put a set of standards in place, a framework, an architecture to enable interoperable networking and communications. And by the way, also PNT in cislunar space. And that became LunaNet. It's basically a lunar communications, positioning, navigation, and timing architecture for interoperability in cislunar space. So one of the most interesting things that LunaNet provides, in addition to specifying layer 1, layer 2, layer 3, and beyond, is that its model specifies the concept of a service provider. And LNSP, which stands for LunaNet Service Provider, is the equivalent of the ISPs on the terrestrial internet, the internet service providers, which are basically organizations that offer user communication services. And from now on, I'm going to focus exclusively on the communication side of LunaNet. I'm going to leave PNT to the PNT experts. I'm not one of those. And as you may imagine, the LunaNet service provider architecture defines a series of interfaces. For example, an interface from the service provider to the user, or the user to a service provider, a typical user interface. And then it also specifies different network interfaces, which are the interfaces between or across service providers. So indeed, in this way, if you specify the user interface, users would know how to connect to the network and get network services. And if you specify the network interfaces, service provider 1 can establish agreements with service provider 2 for the exchange of data. So that's the whole premise of it. Now, when we think about data communications and data networking, we know that in LunaNet, we have primarily two stacks. The real-time stack, which is based on IP as a networking layer, and then the non-real-time stack, which is based on the bundle protocol. And then below that, you have all the CCSDS protocols, radio protocols for both layer 2 and layer 1. So with that, last year, some of us had the privilege to go to the White House for the Lunar Interoperability Forum, in which basically we discussed members of the space agencies, the commercial industry, from academy, were able to discuss and present the different views on LunaNet and how to interoperate. And at that time, we presented what we call the set of capabilities that are necessary for a service provider to offer services based on DTN. And at that time, through an illustrative network covering 3 different LNSPs, we basically described the 5 key elements. They are not all the elements, but the 5 key elements. The first one is starting with network management, which becomes obvious. You have a network, you need to be able to manage it. By management, you mean configuration, monitoring, troubleshooting, and management of the life cycle in general. The second is how to deliver a secure user interface, an interface that is secure for the users that are accessing the services, and also secure for the network service provider that is offering services to the user. Then in the same way, how do you establish and how do you manage the inter-LNSP interfaces or the inter-LNSP relationships? The fourth is how do you secure the user applications? Because it's not only about the network security, it's also about what happens, how do you provide security to the user applications? And last but not least is how you enable operations, which is this network is going to be operated in a 24/7 fashion. You need to establish SLAs and how what infrastructure you need to have in place to ensure that to happen. So this is a little bit more than a year old. What has happened since then? Well, number one, some commercial updates. And these are also in good news. I only bring good news today. This is also good news. The first contract requiring LunaNet compliant delay tolerant networking were awarded last year. What that means is that finally, after many, many years, there are contracts, and these contracts are basically issued by the space agencies now because they are funding this first wave of LunaNet, where they are requiring support for DTN. Where? Well, first is on the core relay services, including the ground infrastructure, NASA, and this is the Lunar Communication Relay and Navigation Services, issued a contract to Intuitive Machines to basically develop and deploy up to 4 satellites, and with that offer a relay service. And I'm emphasizing the word service because the whole idea is that the space agencies are driving the business, the model, the commercialization model to be a service that the space agencies are going to consume, not necessarily own. In addition to that, NASA, which I think was pretty clever, also issued a contract for the initial feasibility study and prototyping demo phase for the Lunar Terrain Vehicle Services. This is the lunar rovers. And they issued 3 contracts, Intuitive Machines, Astral Adventuri, and Lunar Outpost, in which, guess what? DTN is also required. But in this case, DTN is required think of it as a user service. So LCRNS is the network side, LTVS is the user side. So you start seeing that the whole idea is creating the demand and the initial infrastructure to set this up, which is fantastic. And then ESA, as part of the Moonlight project, also awarded a contract, the initial contract for communications and PNT to Telespazio. And the goal there is to, again, starting with 1 communication relay satellite, basically following the LunaNet architecture to deliver interoperable services. So long story short, you see that there are, now this is in motion. Companies are designing, their networks, and, fortunately, hopefully we'll see those networks up and running and deployed all in the second half of this decade. So that's the commercial update. Now let's look at the network architecture updates. And this is not an exhaustive list. So if you have been working on something that is not listed here, it's totally fine. I just wanted to illustrate that there is activity happening the same way as Felix, listed all the activities that ESA have been working on. Very important things, right? On the previous slide, you saw, and I commented, that NASA and ESA awarded contracts. And typically when you award a contract, where you have a requirement to follow or to implement a specific protocol, better that protocol is a standard, right? So what has been happening in the last, let's say, 12 months of standardization, it's pretty much a rush to complete the standardization process for specific documents that are bound to those contracts. The first one, LunaNet. LunaNet, if you have been following LunaNet, now we're in version 5. In version 5, which was released in January, this is the first time where they baseline a LunaNet 1.0, because they said, hey, there is a point of time, we need to draw a line so that the folks that are implementing these contracts or working on these contracts have a clear reference. And that became LunaNet version 5. which is the 1.0. And when it comes to DTN, things that are important, there is a final list of convergence layers for the bundle protocol. There is also the set of interfaces required for the ground systems. So it basically makes the thing more, or the requirements more specific. CCSDS has been also making good progress in twofold. The first one is, again, rushing to complete some of the key specifications. I started with a bundle protocol 7. It's now an orange book. So now we have a reference that people can look at peaks and conformity, and then working on other areas that are relevant, whether it is to LunaNet 1.0 or later. That's something to, that's still a question mark. But continue progressing on the standardization with things like, BIBE, there is an orange book, the QoS extension blog, and then other kind of things deciding like bundle fragmentation and things like that. And then on IETF, the IETF progress continues. I think that the thing that is worth mentioning above all is DTN management, which is one of the big open items in the state of the art. Now the DTN management architecture is an RFC. It's RFC 9675. It was released. And then the DTN working group is working on a bunch of drafts that are related to BPSec, more context types, specifics on DTNMA and how it integrates with terrestrial protocols and the likes, BIBE, and then other things like BTPU and more. So there is good activity. As I said before, part of the activity is related to LunaNet 1.0, and part of the activity is related to what is going to happen in 1.1, 2.0, etc. And the third part of the update is recent missions and experimentation. I won't spend much time here, other than that to say NASA has DTN as an operations capability in the ISS. There are, I think, 20-something, 30 payloads in the International Space Station that uses DTN. And NASA PACE, which is has a great name, Plankton, Aerosol, Cloud, Ocean Ecosystem, Earth Observation Satellite, which is in LEO, became the first use of DTN in a Class B mission. Class B means low-risk type of mission. And it launched in 2024, and it's still operational. I think it's going to be around until at least 2027 as a, they fund the mission, and then it has a lifespan up to, I think, another 6 years or so. I think it had propellant for 10 years, or give or take. And then in terms of recent experimentation, many of us are experimenting on this, but things that are worthwhile to consider, worthwhile to mention, KPLO, which is the Korean Pathfinder Lunar Orbiter. It became the first satellite using DTN in cislunar space. They did the first video streaming using DTN. It was a K-pop song, just, like it. And although the DTN experiment completed successfully, the satellite is still there doing, science. Then I won't touch much into it because Felix talked about the lunar ice cube test. It was supposed to be a full mission, but unfortunately the satellite was lost, or they didn't make a good contact. So they replayed the telemetry and emulated these on Earth to validate the interoperability. It was a great demonstration. And last but not least, and we're going to be talking about this tomorrow, at our technology demonstration in the ISS, we operated a network using the service provider, the LunaNet service provider architecture for 18 days, exercising management, data transfer, and other stuff you're going to hear tomorrow. So now, where are we from last year? Well, pretty much the capabilities haven't changed. When we need network management, things that have popped up more recently has to do with how do you manage security policies in an internet working environment in which you may have different implementations of the bundle protocol. How do you manage the QoS policies and what is the format of those? And that's where there are some proposals in place, but there is not firm decision on what is to be used. So for example, at the Spatiam, we use in the security policy, oops, sorry, let me jump here. In the security policy management, we use a specific format that was proposed by Eddie Rain and Sarah for security policies or BPSec policies for space networks. We implemented that. It works. It is also implemented in ION at the node level. But this is just a format. So it's something that, again, has to be thought for standardization as well. Then the other thing that continues to be extremely important is how to deliver a user to LNSP interface, a secure user to LNSP interface. In reality, at the bundle protocol layer, there isn't a great answer, or there is a good answer, but it's basically the use of BIBE, bundle encapsulation. And the reason is the relationship at the bundle protocol layer is peer-to-peer, very similar to the internet problem when you have a user and a network, which is how you secure that entry point. So the proposal is still to use BIBE as the gateway, as an element to isolate the user context or the user domain and the network domain. So for example, you can have a specific BPSec policy, which is a user policy that is end-to-end, and another security policy that is a network policy that only happens within the network. It also has to do with QoS. The user might be signaling any sort of requirements for QoS. They might be marking their bundles with, whatever extension block, but at the end of the day, the SLA you have to provide. So how do you perform isolation? Again, the use of BIBE allows to separate the user and the network lane. Managing internal LSP interface. This is a very interesting topic because the way it is being resolved right now is there is a huge database of parameters that CCSDS, actually SANA, maintains, which is supposed to be the parameters that you exchange with another service provider. Of course, that's exchanging emails and exchanging, spreadsheets are as good as what that is. So there is more open room for automation in the means of performing having registries in the same way as with BGP, for example, that there are registries where basically service providers can go and look and even read information to basically configure their interfaces. And when we think about operationalization, the thing that we keep focusing on has a lot to do with contact plan management. Remember that DTN performs time-based routing, so it needs to have an accurate information about the contacts and how you propagate those contacts through the network. But when I say the network, that includes the administrators. If you look at any mission or user mission, contacts are planned from all the way from the physical layer to tracking and telemetry and commanding of the hardware assets to then command and data handling, and that processes that's a very, very changing and living process. So, for example, on the ISS, we would get a new contact plan every day. And then, you have 40, 60 different contacts and how you update that automatically so that the network stays current and you don't lose communications. So this is where APIs helps a lot as a way to connect distinct systems in ground to be able to orchestrate contact plan management. I'll talk about that tomorrow in more detail. So with that, this is the summary I wanted to provide you with, which is I mean, building DTN capabilities on an LSP is still an ongoing topic. Very important to implement network management. We have made good progress on security policy management, and but this applies to other type of policies like quality of service as well. Key to deliver security on the user to LNSP interface, and then managing the inter-LNSP relationships or the network interface, and then important to secure the user applications and to enable operations. So with that being said, any questions, any comments?
Thank you, Alberto. Would you mind coming just for people to see you asking the question live? Thank you.
It'll be a stupid question, of course. When you say security policy, are you purely talking about the BPSec policy, or are you talking about general kind of sort of firewalling, traffic shaping, as in terms of flow control rather than?
Yeah, awesome. Great question, Rick. So in general, it's the whole security policies. The BPSec is part of it.
Yeah.
It's one layer of it. And I'm focusing on that is because BPSec is a standard. So people understand when you go step above that, it becomes a little bit more interesting in the sense that think of the following, right? Right now, the way you control applications on bundled protocol is whether you open a service, service ID or not. And then how do you map a service ID with a specific application? So there is that part of the policy, that part of the magic is still not standardized and very proper.
She's got
Nope.
Somewhat more question. Otherwise, I want to jump in on that one as well, because I find it very interesting. So you're trying to define an interface between what is a user segment and the network service provider, Lunar, whatever, right? And of course, you need to manage that. But the DTNMA, right, is more like an horizontal, non-hierarchical type of management. Of course, there is a centralized entity, right? Right, but you don't have a user, let's say, segment and a network segment, right? So how do you make these coexist? I mean, the definition of a user asking for a service, the network providing the service, and DTNMA as a way of configuring both segments. The question is for Alberto.
Come here. That's a very interesting question. So you would tackle this as two separate domains. Okay. So on one hand, the responsibility of the service provider is to offer an SLA and adhere to it. Mm-hmm. So you configure your policies using management. So for example, you can have a specific manager endpoint that is just a manager endpoint for the network elements. Mm-hmm. Okay. Then what the user has, the assumption we use is that the user is not even managed by us. Okay.
Okay.
It is the responsibility.
So DTNMA is not touching the users at any moment.
No, it could, but the assumption is, if you apply the zero trust architecture, is that you don't trust the user. You don't know what they are going to do. You have a service level agreement. That's what you offer, and then every abuse or depends on the user what they're going to do, and the gateway needs to be smart enough to protect the rest of the network from it.
So contact plans don't flow to the users.
Not necessarily. It could if you have a layer, because the way you implement management, DTN management, is that you're going to have a layer even on security. You have a security layer for the users. The same, you have a security layer for the users if you decide to do so, because that node might not be yours. So, or managed by you.
Of course.
So that's the approach.
Thank you, Alberto. Thank you.
A very quick response about DTNMA. Yes. It is a way of managing a device. What that device is doing is kind of irrelevant to DTNMA. So all your questions, brilliant. Ignore the DTNMA part. That's just a mechanism in order to activate.
It's agnostic whether it is a
configuration system.
Makes sense. Okay, perfect. Any other questions or comments? Otherwise, we appreciate. Thank you, Alberto.
Thank you.
Right, we move to our next speaker. Let me prepare things up for Teresa here. Let me share my screen here. Oh, all right. So let me briefly introduce you, Teresa. Yeah, so our next speaker is so let's welcome Teresa Algarra Ulierte. Teresa is a PhD candidate and research fellow at the Hamburg University of Technology and the European Space Agency, focusing on space communications. Her network centers on quality of service over delay disruption tolerant networks, and the title of Teresa's talk is What Channel Analysis Tell Us About Quality of Service Needs in Space DTN. So thank you, Teresa, and welcome.
Thank you very much. I'm very happy to be here. If anyone has been in any of my presentations before, which I think a lot of you have, I talk nonstop about quality of service. So I thought I would switch it up a little bit this time. And this presentation is going to be a lot about channel modeling, channel analysis, errors analysis, and then a little bit about quality of service in the end. So I hope you enjoy it regardless. So I'm not saying anything new. We have space communications, which present specific challenges. So we have the very long delays, high error rates, intermittent connectivity, and all of those specific challenges are the reasons why we have DTN and bundle protocol, what unites all of us. And then it's always the DTN and BP, there is a need for QoS, there's a need for QoS. However, something that is very important to take into account is that the same way that for space communications, we needed space-specific protocols, we couldn't just blindly copy the terrestrial protocols. For DTN and BP, we also cannot copy QoS approaches that we have with terrestrial communications. We really need to tailor them to the specific needs from space needs. So how can we know what quality of service is needed for space communication? How do we know what the most prominent challenges for quality of service are? So what we do is, of course, we go back to the drawing board and we go to take a mathematical approach and we start with link modeling. So this Gilbert-Elliott model is the standard in literature for losses. So you have two possible states, either you're in a success state or you're in a loss state, and then you have a probability. If you have a very good channel, your probability of staying in a success state is very high. If your channel is not so good, then you will have a high probability of loss, and therefore of also staying in the loss channel, that is of having several losses in a row. So now we have to put our detective hats on and try to use induction to see if this type of model also works for space communications or to which extent. So where can we get some data to really analyze what happens in space communications? And here I'm presenting the data from 3 amazing missions. The first one is BPSec-MLS, which is a joint mission between European Space Agency and the Japanese Space Agency. It was launched in 2018 and it's on its way to Mercury. We will also see some data from the Solar Orbiter, which was launched in 2020. At first I wrote the goal is to reach the sun. It's not really going to reach the sun, it will just get close by, thankfully. And then we will also see some data from JUICE, which Solo is ESA and NASA, and JUICE is only an ESA mission, which was very recently launched. You will not see a lot of specific data mission, but I think that the year where they were launched is relevant in the data. So how does this data look? The first thing that we need to look at it is when do we have passes? So we have passes, so the mission is transmitting, then at some point it stops, then it's transmitting again, and it stops, and so on. And that's what we call the passes. When we look at the passes more in depth, we can see that sometimes we have, like in green, a lot of well-transmitted frames, so it's frames that were well arriving and decoded, and then in orange we have frames that were either lost or disrupted and they could not be recovered. So all of the frames that I will talk about as error frames are already past any kind of recovery hopeful. So we can also classify this data in how bad was a pass. So we can have passes that were very good, so with less than 1% of error. We have passes that were very bad, so basically the entire pass was lost, except maybe a couple of frames were not even. And then we can have anything in between, from like 10% to 50% to 90% error. So then we're going to look at the empirical validation. when we look at the emissions, this is what we get. In green, we have less than 1% error. In light green, we have less than 10% error, and so on until dark red, where we have basically lost passes. Because thankfully, these missions have very high success rates, it's not so easy to look at this picture, so we're gonna assume we don't care about the success, and we're just gonna look at the errors. So there we have something like, okay, in most missions, we have either less than 10% errors or lost passes. So here, for example, we have a lot of lost passes. We have here a lot of passes with low error rate, but still some error rate. And we don't care too much about the actual numbers. We care more about the proportions. Because when we look at this, for example, this is Verbetti Colombo expand, we see that when we have less than 10% of the passes, we can assume that these are short error busts or even uncorrelated errors. And when we look at the higher part, where we lose over 90% of the passes of the pass, we have very bursty errors or even correlated errors. So maybe a better description for the channel is having a clear separation between uncorrelated or short-term errors and correlated and short-term long-term errors. So this would be more than 50% of errors in a pass. This would be probably less than 10%. Now, let's go back to the data and see if this definition still applies. We can look at how the errors behave. So this is the burst length distribution. Again, if we look at the whole picture, we really don't see much here because we have some burst errors that were extremely long. So if we cut it a little bit and put it in logarithm scale, we can see that we have, some burst errors a lot of burst errors, that last very little, and then a lot of burst errors that last a very long, but they actually all have different lengths. So if we look at it in a cumulative distribution function to make it a little bit easier to understand, what we see is that we have many short bursts, and so much so that 95% taking into account that a pass is anywhere between 3 and 8 hours, 12 seconds for a burst is relatively short. And we have some few but extremely long outages. Here we are at 60 seconds and still the CDF has not reached 100%. So the next logical question is, why is the behavior between errors so different as to give such different error burst lengths? So if we take a closer look at the data, these are some selected passes where we can see in green the successfully received frames and in orange the wrongfully received frames or the frames that we know we were expecting and got lost in the way. So we can see some short bursts, relatively short bursts. We can see much longer bursts of several hours. We see what we can classify as single errors or very, very short bursts. And we have whatever is happening there. I will spoil it to you. This was when Baby Colombo was getting close to the sun, so this was solar conjunction. But this error frame kept me awake for a couple nights. So the conclusion is that different error sources found different error probabilities, different error patterns, and specifically many different lengths. So in order to see where all of the possible errors come from and model them, we need to classify them much more specifically than just long or short. So we can have errors caused by rain. If we're taking into account optical communications, we also have to take into account cloud coverage. We, of course, have space weather, which comes in two forms: solar flares, which is very unexpected, and we have solar conjunction, which is something that you can specifically plan for. And that's why when I say that these frames or these passes were receiving a lot of interference from the solar conjunction, the team knew very well that these frames were probably going to be lost. And they were saying, okay, if we get 10% of the frames, then that's at least good. So I will not model solar conjunctions in this Markov chain because it is a scheduling problem, let's say. So from space weather, we will only understand solar flares as of now. We have antenna pointing errors, which is quite a big problem, especially when you have small antennas with a lot of sensitivity. We have warps. We have radio frequency interferences, and we have operational factors. So these are all of the correlated error sources with an asterisk because these are the highest impact and strongly correlated error sources. I hope there's no one who's more of a specialist in optical communications because they will hang me for this. If there are aerosols, K radians, we can just assume that those are either not too impactful or weakly correlated, then we can take the freedom to ignore it. So, ignoring those, we can add all of these things to the Markov chain. So we have to remember again that we have the uncorrelated losses, so the very short single errors, and we, surprisingly, still have a chance of success. So when we turn all of this into an extended Markov chain, we get this amazing spider web, which is honestly very beautiful, but also a little bit complex. So you will think, oh, is that all the complexity? Well, not really, because the probabilities are not static. They are all time dependent. If it's raining, I mean, it's going to be raining for either 10 minutes or 1 hour, but there's a certain probability that there's going to be raining for longer or shorter. So how are all of these error sources modeled? So starting by the solar flares, which is, in my opinion, the easiest one to model, they are dependent on time as in duration. So solar flares are minimum 6 seconds, maximum 60, peak at 21 seconds, whatever. They are dependent on the location. So if you're somewhere here, protected by the Earth's magnetic field in that moment, this solar flare is not really going to affect your spacecraft. However, if you're here, you're going to have a tough luck communicating back to Earth. And it also depends on the solar cycle. Depending on which year we're on, we're going to have many more solar flares than in a year when the solar is at the minimum. Moving on to rain and cloud coverage, they are dependent on, again, time. Probably we have that if it's rainy or cloudy, it will stay rainy and cloudy for a certain amount of time. We have dependency on the time of the year, if it's winter or summer, and the location. But we don't only care about the location in the sense that, oh, I'm in Germany or I'm in France and we have X amount. If we're talking about optical communications, we really have to take a picture of the sky from the ground station and say, okay, I detect 80% of clouds at this exact moment. And that is the kind of accuracy that we need. And of course, we are also dependent on frequency band. X band is not going to be much bothered by rain. However, Ka band will actually suffer quite a lot of attenuation. Moving on to antenna pointing errors and RF interferences, I've grouped these two because they're both dependent on duration, on the frequency band. So the pointing accuracy is going to be much higher for higher frequency than for lower, as well as, of course, RF interference is going to be highly dependent on which frequency band you are currently finding yourself in to see where the interferences come from. And they are both dependent on the mechanical characteristics of the antenna, the receiver, the transmitter, etc. And then we have operational factors, which is something that I found out while analyzing all of this data. There's a lot of like, oh, ground station operational downtime because of something obscure. And they appear, but they don't seem to depend on much, and they must depend on something, maybe like how old the ground station is. But this is a little bit of a big incognito, which is like the biggest random factor that I have found. So now we have a Markov chain that is 8 states big. It's dependent on time, but as well, it's dependent on location, time of the year, time of the solar cycle, frequency band, and mechanical characteristics so far. And these are just the highest impact factors and the ones that are strongly correlated. So I, of course, have some open questions that I'm currently working on, which is, well, all of these like very like time-dependent and complex Markov chains are these niche topics. So how much complexity do all of the other things add? Which leads me to the question, well, is it really feasible to mathematically formulate this? It would be quote unquote easy. Like once you have the information, it's easy to add it to a simulation, but how can you really add it to a Markov chain? And another question that would come up is, well, what if you have rain and the solar flare at the same time? Do you care that you have both at the same time? In the simulation, you don't really care so much. That if you're trying to mathematically model this, is it really a Markov chain if you have rain and solar flares at the same time? And the question that also doesn't let me sleep, what are operational errors and where do they come from? They come to chase us. Thankfully, we also have some conclusions, which is the good news about this presentation. which is that we can really get out of here what the biggest problems or what the biggest effects on the communication link are, which is that we know that we have intermittent connectivity with DTN, and now like on top of the planned intermittent connectivity, we have error bursts that might be short, but also might be very, very long. This will, of course, lead to bottlenecks. So something that is absolutely essential for DTN is some type of congestion control. This congestion will also lead to full buffers because satellites or relay nodes or DTN nodes are unfortunately not infinite. So packet dropping guidelines also need to be defined in order to avoid random bundles just being dropped because no space anymore. And with so many causes for losses, we of course have the possibility of having high error rates in the link, although it's not always like this, but it is always an option that the link will suddenly become very lossy without any previous information about it. So having the possibility of indicating whether retransmission is meaningful or not, if your bundle is lost, is also necessary. So this is where we come to the solution, and this is what I normally present. So I have derived some quality of service requirements like congestion control, which is a very broad topic and a whole research area on its own. But I will, with the excuse from everyone, simplify it with two terms. The first one is priority and the second one is fairness. If you have a very big bottleneck, let's say you have infinite queues, you will need a way of saying, well, this bundle is more important than the next, and therefore it needs to be transmitted at the earliest possible time, whereas, I don't know, this image of a rock that the rover took can wait. However, not only prioritization is important, but also fairness. Because if you assume extremely long bottlenecks or even infinite bottlenecks in a mathematical model, your rover at some point will say, well, I've been waiting for a very long time. I would really like to have the chance to transmit this picture of a very cool rock. So you also need a way of giving all of the users the possibility to transmit. The second QoS requirement is reliability. So when we have high error losses, there needs to be a way of keeping tracks on what gets sent and what doesn't. There's also the age of information, which is something that wasn't a direct conclusion derived, but it can get derived from all of this, which is if we have very long bottlenecks, and we have, let's say, a sensor network that tells me the temperature on the moon, and we have bundles coming in every 5 minutes. At some point, you're not going to care what the temperature on the moon was 20 hours ago. You probably only care in the last hour or in the last 5 minutes. So it's also important to be able to address the age of information of the bundles. And lastly, storage and resource utilization. So the buffer will get full. It is nice to model infinite queues mathematically, but we cannot count on them in real life, thankfully. So the solutions that I will present is that for congestion control, we can implement traffic prioritization. As Fred presented in his presentation, actually, we have been working on a model that has traffic prioritization that is divided in two ways. So you have high-level classes. So I say my bundle is critical and therefore it must go in any case. But then when you have bundles of similar priority, there would be a fairness approach or a weighted queuing approach that is volume-based. The one thing about bundle protocol that makes it a little bit different from other traffic prioritization approaches is that all bundles are differently sized. In other protocols, all of them are, let's say, 64K, for example. In bundle protocol, you can have anything between 64K and 50M. So if you just say, well, one bundle per priority, that might be extremely unfair. And that's why a volume-based fairness approach is much more meaningful for the wide variety of sizes that bundle protocol presents. For reliability, we have retransmission. That doesn't mean that we innovate in any way retransmission, but that it is important to indicate, I want this bundle to be retransmitted if it's lost, and to say, well, this was just a video. It doesn't make sense to transmit a frame 3 hours later. I really don't want the transmission. Just send it, and if it gets there, it gets there. For age of information, the literature had a very good approach, which was latest only delivery, in which you can indicate where I only want the last bundle of this kind. So, for example, this temperature sensor network, or I want the last 5 bundles, or I want the last 24 hours. And for storage and resource utilization, there is the bundle retention flag, which can say, well, my bundle is really not that important. It's similar to retransmission, but for being dropped. It's okay to drop it if the buffer is too full, or hey, my bundle is actually very important that it gets transmitted at some point. So please keep it. All of this gets implemented in a bundle block, bundle protocol extension block. Oh, I didn't write that so nicely. Bundle protocol extension block, which if we look at the structure of the bundle, we have the primary bundle block, we have the payload block, and then somewhere in between we have a multitude of possible extension blocks. And this would go as the user quality of service extension block. It's named like this because it is defined by the user and only the user. So if I am a relay node and I get a bundle from, I don't know, another planet, I will not be the one to say, well, I think this is critical. Because it can only be set by the user, it also has to be, it has to go with a bundle integrity block in order to make sure that it's immutable along the entire path. So I will skip quickly over this because this is the part of the presentation that I've done several times. There has been previous work showing that this works, so simulating the three-state Markov chain, not the extremely complex one, and showing that these results are consistent with, more or less consistent with what we see in the empirical data, that traffic prioritization works, and that this nested interleaving or volume-based approach to weighted fair queuing is much better for similar prioritization than non-fair approaches. So much so that all of this is currently being implemented or on the way of being standardized as an orange book. So a CCSDS experimental draft experimental specification. It is almost done and it will be published at some point next year. So that's quite exciting. And I am very looking forward to answering any questions, or maybe you can answer my questions, actually.
Thank you, War.
Thank you very much.
Thank you, Teresa. Yeah, do you have any questions for Teresa? Yes.
Amazing.
You can come, you can get up as you wish.
Do they need a microphone?
Sure.
Ideally, yes, so the remote people can pick it up.
First off, thank you, Teresa. I've been following this work for a while. I think it's really important. I think it's great.
Yeah.
As part of my following it, I was trying to understand if you've looked at hierarchical token bucket as a way of achieving fairness. Are you familiar with hierarchical token bucket?
Not with the terminology.
Okay, quick Google search for HTB.
HTB, okay.
HTB, it's how the internet manages, particularly the Linux network stack, manages different levels of flow control, and it's volumetric weight based and with stealing from other layers. To me, it seemed like a really good solution, and I know I've seen inside the Orange Book, so have a look. I'm interested in your feedback.
Okay. Thank you.
Thank you very much for the presentation and the work. It's a very valuable. So we've seen we've seen that things like the transmission, like congestion control, they have they either start or have a negative impact on the health of the node. So sometimes you need to make decisions in respective of what is being signaled to you. So have you discussed any mechanisms as of how the receiving node behaves to a request of such type? So if you cannot honor, for example, any of that, or you have to discard a bundle that has a very high priority for whatever reason, what are the behaviors of that node towards the evening?
Thank you. That's a very, very important question that I have actually worked extensively on, thanks to the CCSDS. So there are two parts to the question. One is the node would like to, follow the indications, but it cannot. And for that, there is always a possibility, right? So for example, the bundle retention or the traffic prioritization, it's all relative, right? So maybe you would like to keep the bundle because it has a higher priority, but you cannot, and that's okay. It's just an indication to how it should be proceeded in case that something goes wrong. So you wouldn't delete a bundle of priority 20 if you have something of priority 21, for example, to be deleted, and so on. For retransmission, it can be that the relay node doesn't have retransmission capabilities or that the link is unidirectional. That's why for the retransmission, there are several classes defined in which you can say, I want retransmission. If there is no retransmission available, you must drop this bundle, which is a little bit of an extreme case, but might be useful in some cases. Or you can indicate retransmission if possible. If not, just transmit unreliably or without retransmission capabilities. Now, the second part of the question is, what if the node does not want to comply with the with user quality of service extension block? And that's why it's called the user quality of service extension block, because we contemplate the possibility of having a network quality of service extension block, which I don't have here, unfortunately, but it would be another extension block. In this one here, or actually here, sorry. And it indicates and says, well, this user is from this company, and this company pays us the normal subscription, but not the premium, which means that everything that is high priority for them is going to be middle priority for us instead of their high priority. However, our premium user is going to have the highest priority. And then with that, it can be circumvented. They don't necessarily need to listen to the user quality of service extension block. What is important with the user quality of service extension block is that the relative position to the same user must be respected. So if you have something that is critical from user one and low priority from user one, the critical should always go before the low priority. But it can be that you have low priority from premium user and critical from non-premium user, and you say low priority of premium user before critical of non-premium user. Yeah.
That's interesting.
Yeah, it is an interesting challenge. So we, at some point, we have to rely on like policy also between different, not only space agencies or entities, but also administrative domains, that they will, to a certain extent, respect what is being said in the user quality of service extension block, or they will have a network quality of service extension block that will go with it. But this will also be useful in the case, for example, for resource constrained nodes, where I say, okay, I'm the gateway node, and I know the next nodes cannot process all of this information. So I will just put something that in their processing can be done. And then when it gets to the exit gateway node, we will see. But thank you for the question. It's a topic that I like.
Thank you very much, Teresa.
Thank you.
So we'll move quickly to our next speaker, to Xisen, who is remote. Xisen, if you can hear me, please feel free to take control of the screen, and I will briefly introduce you. Our next speaker is Xisen Tian. Xisen Tian is a PhD student studying applied cryptography at Naval Postgraduate School in Monterey, California, under supervision of Dr. Britta Hall in the Applied Cryptologic Engineering Group. His research areas are in secure group communication, security for space system, and post-quantum cryptography. Xisen is also an active member of the Internet Engineering Task Force and CCSDS, two organizations that produce standards for Internet and space communications. Xisen, if you can unmute and take over screen sharing, the floor is yours.
Hey, sorry, I have to close and reopen this real quick because the settings won't let me share my screen. I will join right back.
No worries.
1 sec, sorry. Hello, I'm back. Hopefully this works now. My apologies for that.
No worries.
Okay, can y'all see my screen okay?
Yeah, we can.
Okay, great. Yeah, so I just want to begin by thanking everyone for attending my talk, and also I especially want to give a shout out to the conference organizers for letting me speak both here at the STINT workshop as well as the WISE conference. If some of you came from that, this will be a repeat of that. So this is encore presentation. This is the BPSec-MLS Asynchronous Key Agreement for Space Communications presentation. I'm Xisen Tian, and this is joint work with Paul Westland. So to provide a background on our problem, we had done previous work to show that a lack of an integrated standardized key agreement mechanism for BPSec creates challenges for security, interoperability, and scaling in securing bundle-based communications. Luckily, there's this new standardized protocol called Messaging Layer Security Protocol, which provides continuous group key agreement for specifically these kinds of issues. And its key benefits are that it's, first of all, standardized by the IETF, and it is formally verified through extensive machine and cryptographic analysis. It provides forward secrecy, post-compromise security, and also has logarithmic scaling in best case scenarios, and post-quantum amortization available as well, meaning that we can implement post-quantum cryptography in MLS without paying the full post-quantum price. The ION suite of protocols, the Interplanetary Overlay Network, is NASA's implementation of delay-tolerant network architecture and related protocols, and is what we used in our implementation experimentation. Okay, so for those of you who haven't heard this spiel before with what MLS is, it is basically this continuous group key agreement protocol that uses that ratchet tree in the center here, taking everyone's public keys and computing a group key at the node, at the root node there, which allows you to derive encryption keys off of to be used for application messaging. And this differs from a traditional pairwise kind of group channel that you might see with Signal or TLS, in that in those settings, you actually have to establish a key with every member of the group, and then they all have to do it again with each of the other members of the group. And so that quickly balloons to a polynomial growth size, growth rate of n squared, which is highly undesirable if you're going to scale. So this kind of group key evolution mechanism that MLS enables forward secrecy and post-compromise security guarantees. Now, this means that previous communications will not be affected by a compromise in your current epoch's communication. And similarly for PCS, if you compromise a particular message key right now, once you update your group keys, your future communications will not be affected by that compromise in the past. So the PCS concept is actually very unique to MLS. It is not available in TLS. It's something that is inherent in continuous key agreement protocols such as MLS and Signal, for example. And so MLS, again, can utilize quantum-resistant cipher suites. That's that post-quantum cryptography. And then, again, has the ability to have those costs be amortized. And again, I want to hammer in that MLS is standardized and widely deployed, as opposed to other previous work that have proposed ways to do key exchange in space scenarios. So yeah, MLS is used in Wire, it's used in AWS Wicker, it's used in WebEx by Cisco, Ring Central, as well as Blue Sky is developing their own kind of decentralized MLS network with the help from a company called Germ. Okay, I want to foot stomp that this tree here is a locally computable logical tree. It is not something that is overlaid into the network hierarchy. The intermediate nodes are computed from, again, the public keys of individuals in the group, which are represented as the bottom leaf nodes in this tree here. And again, that group key is derived at the very top, that root node on the top of the tree here. All right, so here is a high-level kind of overview of what our design attempts to do. So with the current standards written for BP and BPSec, we're mainly relying on pre-shared keys. This is how most people implement it. It's not, the standards don't really restrict this use of pre-shared keys, but traditionally when we launch space vehicles or payloads, we preload them with crypto keys, and they stay up throughout the life of the mission. And this can be pretty disastrous if any of those keys are ever compromised. You have no forward secrecy or post-compromise security guarantees, meaning that if any one of the pre-shared key sets are compromised, everybody who used those pre-shared keys will have their security be similarly affected. So here's where MLS comes in, where it allows you to dynamically add group members, remove group members, and update keys as needed. And we do this by putting MLS handshake messages inside the payload of a bundle protocol, of a bundle, and use those keys that are derived from those messages to help BPSec either encrypt the bundle, the BCB's bundle confidentiality blocks, or help with data authentication with the BIBs, the bundle integrity blocks. And so this is essentially how MLS can accomplish this, and we do it all on top of the litter transmission protocol for a kind of full DTN stack here. And so here's kind of what it would notionally look like. You have the MLS messages in this payload block here, and those messages are processed by the receivers who are part of the group to be able to generate keys then used to protect used in the operations rather that BCB and BIBs use to protect their target blocks. So that's going to be a symmetric key encryption, as well as the message authentication code generation for data integrity. And so, yeah, these MLS messages come in a variety of forms, but the first couple ones listed there, add, welcome, external, join, proposals, all those are proposals, so suggested changes to the group, and then a commit message actually tells the group to implement those suggestions. Okay, so here's the notional scenario that we've adapted from CCSDS. Rationale, scenarios, and requirements for DTN in space. It is kind of what we then reinterpreted as a leader-subordinate group control, and it's aligned to the fact that the mission control there in the center is well connected with the other units around it, who can then reliably send messages to the outstations. And for us, this leader acts as the MLS group administrator. That's to help get around the issue of potentially conflicting group synchronization messages. So we utilize that leader as the delivery service, which is responsible for deconflicting commits and changes to the group via the ordering of proposals. And then we also utilize this MLS group administrator as the authentication service as well, which the authentication service in MLS associates identities to public keys. Now, that scenario in the last slide can be implemented in a couple of ways. You can have basically option one, which only allows the leader to make group state changes. So only the leader does that, and none of the subordinates are able to add or remove users or do updates on their own behalf. Option two allows subordinates to be able to update their own nodes via a proposal, a suggestion, but ultimately the leader is the one who commits to those suggestions. And then option three kind of is a laissez-faire kind of, everybody is allowed to commit. So anybody in the group can make group state changes via proposals and commits. And so these different options actually yield very different security outcomes as well as efficiency outcomes. And so in option one, because only the leader is doing proposals and commits, there is no PCS for subordinates. So there is no post-compromise security or the ability to heal after a compromise of the group key for a particular subordinate node. Now, this might not actually be a big deal for a particular use case because, hey, maybe the users themselves are located on the moon and there's no actual way of compromising them. And so that threat model there is adjusted. Now, this also leads to, unfortunately, the worst tree configuration. And what I mean by that is that you'll notice in option one and option two here circled that the intermediate nodes EFCDG or EFCG are blanked. And in MLS, this kind of configuration essentially collapses the tree down to essentially a linked list, so that whenever one there needs to send an update to the group, they actually have to make commits they have to send their commits encrypted under the public keys of each of the individual members. So you're losing that logarithmic efficiency of a fully populated tree because only the leader is able to submit commits. Commits are what allow these intermediate nodes to be populated. Now, in a subordinate proposal option, that's pretty much the same thing. But you actually gain PCS now because subordinates can update their own leaf node, and then the leader just commits that to the rest of the group. So you get PCS for everyone and FS, but you actually do incur a group state synchronization overhead, meaning that you have to somehow determine the order of proposals if they ever all arrive at the same time or out of order, which is classic kind of thing for DTN environments where messages can arrive late or out of order. And so ultimately, this still lets the group leader to make this decision on, 2 comes before 3, 4 comes before 8, if they all kind of arrived at the same time or are out of order. So you need to have some kind of external policy then to determine the adjudication of proposals in this option 2. Similarly, for option 3, that's also the case. If everyone is able to commit now, well, now the leader isn't responsible for adjudicating these commits. You have to have some kind of a stronger external mechanism to do this commit sequencing. And so that could be done on a schedule basis. For example, for a certain amount of time, only 1 is allowed to commit, or 2 is, and then 2 is next, then 3, and then 4. Or, it could be based on some kind of hierarchy pre-established within the group when they have conflicts. Now, so option 3 does, give FS and PCS for all, and it actually results in the best tree configuration because everyone is able to commit. In reality, you can actually, in a real mission, you probably wouldn't stick with each of these options the entire time. What you could do is you could launch, you could, at the time of launch, establish your group in a way that populates the tree fully. So having everybody who's added just commit once, and then after that, you can just have the leader do the commits. So you would have the best tree configuration. You wouldn't get great PCS because after that launch period, you may decide to allow only the leader to do kind of the adjudications of commits and proposals. So some kind of option 1, option 2 hybrid to optimize for the DTN scenario where you can get things delayed or disrupted. Now, this is all implemented in a MLS daemon that we created in our experiment to interact with the ION suite. The APIs used for ION were not modified. The MLS daemon wasn't modified. The goal was to demonstrate the feasibility of BPSec as it is, MLS as it is to be combined, and measure the empirical data of the MLS overhead across various group sizes. So the way that this works is we have these MLS bundles that get delivered to a BP capable node, who then takes that MLS message, sends it to the daemon, which does that group key computation via the logical ratcheted tree. It then exports the key back into ION to be then used by the BPSec logic to either encrypt data or to apply message authentication codes to data for use in BPSec. Okay, so the result of the experiment was generally linear kind of growth across various group sizes. The top shows the cost to join a group, and the bottom shows the costs to update the group via the option 1 configuration, which represents the worst kind of tree you can have, and option 3, which is the best case scenario for a tree. Now, realistically, your tree is going to be somewhere in between option 1 and option 2, which is why we showed both here, because you're going to be adding and removing users or having some group members commit or some others not commit. So our results show this kind of linear growth where the option 3 here, in terms of processing time, outperforms option 1. But in terms of memory usage, option 1 outperforms option 3, and mainly because, in option 3 you have that fully populated tree, which has all the intermediate nodes populated. So there's a lot more there's a lot more resources that it needs to construct that tree and update that tree periodically. As far as message size, though, we do see a logarithmic growth. So this has implications for bandwidth utilization. We see that in option 1, this is a logarithmic scale, so that blue curve that you see is actually a straight line on a normal y scale, and so that increases linearly because, again, like I said earlier, you have to make separate encryptions for each group member in their group updates. Whereas in option 3, you can utilize the fully populated tree to only update strategically to only encrypt to the intermediate nodes in that ratchet tree, so that you're reducing the total number of encrypted messages being sent. So that's how we see the message size reduction there. So upon a closer examination of that, we see that logarithmic sawtooth kind of behavior in this data. And this is largely because we have measured the message size at the last member to join an MLS group. That last member to join an MLS group, that its position, of course, changes as the group size grows in the MLS tree on the bottom leaf nodes. So when the tree expands an additional layer to accommodate for a new power of 2, for example, from 8 to 16, and you're the 9th member added, you actually get all of a sudden a jump, an increase in performance, because you are only one distance away from the root node at that point instead of several layers down. And so, but in that case, you're also getting your own individualized encrypted message. So it's a little bit mixed there. So ultimately, what this is showing is that it is showing what potentially any member in the group could experience in terms of their total bandwidth consumption for message updates. So because we've measured at the last group member, their position, since it changes throughout the growth of the group, this graph shows potentially what every other member who have varied positions in the group could experience. So our analysis shows a general linear relationship for processing time, memory, the RAM usage, bandwidth for adding a new member, all for all because the welcome messages, which are used to add members, they contain the entire ratchet tree as well as individualized ciphertexts. And those stats grow directly proportional to the group size. And then, oh, am I still on? Did you lose me?
No, you.
Oh, okay, great. So the results for updating a member's leaf node, those are a little bit mixed, as we just saw, with the linear stepwise processing time pattern, as well as the linear stepwise memory usage, and then also the mixed results for the bandwidth in terms of that linear growth for option 1 and sawtooth logarithmic for option 3. So in conclusion, we provide the first implementation of a continuous key agreement protocol for delay tolerant networks. And our implementation is in compliance with both BPSec and MLS standards. Our results show a generally linear scaling in computation time and memory usage, whereas logarithmic scaling is observed only under ideal group configurations. And so this is consistent with previous work, although not necessarily consistent with MLS's advertised logarithmic growth. That's why it's been asterisked throughout the presentation. For future work, we would like to create a draft standard for this, for the inclusion of MLS into BPSec rather than apart from it, like it is currently in this implementation. That includes making MLS extension block or admin record to house the MLS messages. And that should be a more seamless incorporation and would also allow you to simultaneously send encrypted or integrity protected payloads. The use of MLS extensions is also being looked at for cross-layer support. As we saw earlier with the presentations of a bundle protocol being used with IP or used with other kinds of network layers, that it's important to enable group agreement on certain parameters from those different layers. So that's what that extensions work is attempting to do. And then there's also alternate MLS configurations that could be useful for DTN scenarios, such as decentralized MLS, which uses a eventually consistent style delivery service that would kind of be more friendly towards that option 3 configuration that we talked about, not needing a leader to adjudicate things. And then a paired MLS is also an important construct in that allows members who can't update themselves be able to be updated by other group members. And then finally, there's the incorporation of post-quantum cryptography in MLS. And this goes to essentially doing hybrid cipher suites of post-quantum and traditional confidentiality and authentication guarantees in MLS, as well as that amortized combiner that I alluded to earlier. That's what allows you to reduce the costs of the MLS operations, the post-quantum operations. Okay, so that is all that I got. If you have questions, my email is here on the screen, and then my our code is also available on GitHub as well.
Thank you very much, Xisen. We had a little bit of audio issues on this side, so we were able to follow half, I guess, but we appreciate your time. And I don't know if there is any question here from the audience that we can pose to Xisen. We have Alberto here that wants to ask a quick question.
Okay.
Hey, Xisen, can you hear me?
I can hear you. Yeah, a little bit muffled.
Okay, let me get closer. What about now?
Okay. Yeah, I got you.
Awesome. I have a question on the, did you simulate any environment in which you introduced delay and disruption? I'm interested in to see, things like convergence and, how does it look in a, let's say a traditional scenario with disruption?
No, we didn't include disruptions in this. We utilized LTP to send data. We didn't introduce any kind of major delays. It can be introduced. Our code does allow that, and Ion does have that built in as well. But we didn't test for the effects of delays and disruptions in particular.
Okay. Thank you.
Yeah.
Okay. Thank you, Xisen. I guess we give you an applause here from the room.
Okay. Thank you.
And yeah, so with this, we conclude this.